Hey everyone, and welcome to this explainer. Today, we're diving into a critical behind-the-scenes hardware shift that's quite literally keeping the entire AI revolution from melting down. We constantly hear about the incredible processing speeds and massive data capabilities of modern AI chips, right? But there's this invisible barrier threatening all of it, and it's power delivery. So today, we're unpacking the fascinating transition from discrete to integrated voltage regulators. It's a fundamental redesign of how we actually feed electricity to the most advanced silicon on the planet.
All right, let's jump right into section one, the power delivery problem.
To really understand why this shift is absolutely crucial, we have to look at the traditional setup. For decades, power regulation happened on the motherboard, sitting a good few centimeters away from the CPU. But modern AI GPUs are now drawing a staggering 1,000 amps of current. 1,000 amps. To put that into perspective, that massive load completely overwhelms the traditional distant power designs we've relied on for years. Sending that much current across centimeters of a printed circuit board introduces a huge physical bottleneck. And here's why that distance is a killer. The wiring across the board has resistance. Even a microscopic zero point 0.2 milliohms of resistance becomes a massive issue when you multiply it by 1,000 amps. Basic physics dictates that this creates a zero point 0.2 volt drop. Now, in a semiconductor ecosystem where these chips only run on 0.8 volts total, losing zero point 0.2 volts just traveling across the motherboard is an absolutely disastrous loss of power. It's kind of like trying to drink a really thick milkshake through a 50-foot straw. Plus, that physical distance drastically increases inductance. It's literally a physical wall we hit. Which brings us to section 2, moving power closer with IVR. So how do you beat physics? Well, you change the geography. The industry's solution was simple in theory, but incredibly complex in practice. Instead of the old standard, a discrete voltage regulator sitting centimeters away on the printed circuit board, we shift to an integrated voltage regulator, or IVR, sitting mere millimeters away entirely within the CPU package itself. By moving that final step of power conversion right next door to the processor, we drastically reduce that terrible voltage drop, cut down on inductance, and the power arrives cleanly and exactly when the chip needs it. Now for section 3, the pioneer's dilemma. Seeing how elegant the solution is, you might be wondering, why on earth haven't we been doing this all along? Well, we actually tried. Back in 2013, Intel introduced the fully integrated voltage regulator, or FIVR, in their Haswell generation chips. It was a total marvel. It allowed for fine-tuned dynamic voltage scaling right on the chip, delivering exactly 0.82 volts for the core, maybe 0.95 volts for the GPU, saving incredible amounts of energy. But just a couple of years later, starting with Skylake post-2015, Intel actually scaled this technology back, leaving a gap until the present day. But that begs a really huge question, right? If this integration was so innovative and so incredibly efficient, why did Intel hit the brakes? Why abandon a technology that perfectly solved the distance problem? The reality is that integration came with a massive triple threat of engineering headaches. First up, heat. The power components, specifically the MOSFETs, which are the electronic switches, consume tens of watts all on their own. Putting them on the CPU die meant compounding the CPU temperatures, and the chips simply got way too hot. Second was cost. These power components have really poor area efficiency compared to digital circuits, meaning they required a much larger, vastly more expensive pieces of silicon. And finally, yield. Because they were inextricably linked, a single tiny manufacturing defect in either the CPU or the regulator meant throwing out the entire incredibly expensive combined chip. It was a classic case of a great idea just being a bit ahead of its time. That brings us to section 4, AI demands a comeback. Because you know what? You can't outrun physics forever. Fast forward to today, and the extreme power requirements of modern AI chips like Blackwell, Rubin, MI400, and advanced TPUs have made board-level power delivery completely unsustainable. IVR is being forced into a triumphant return. Modern AI workloads are uniquely violent in their power demands. A chip can go from sitting idle to drawing a staggering 1,000 amps in just 20 nanoseconds. Just think about that time frame, 20 nanoseconds. If your voltage regulator is sitting centimeters away on the motherboard, it simply cannot react fast enough. The voltage drops and the whole system crashes. Only a tightly integrated regulator can respond in the nanosecond order required to keep these things stable. To manage this safely, the industry evolved into a really elegant multi-stage step-down architecture. We're no longer just jumping from 12 volts on a motherboard. Now power comes into the server rack at 48 volts. It steps down to an intermediate bus, then hits the package IVR, and only then is that final ultra-low, perfectly tuned voltage delivered directly to the compute die. It's a highly sophisticated chain of command designed specifically to handle massive current without melting the system. Next up, Section 5, the 3D IVR future. But the innovation doesn't stop at just cramming the VR into the same package. The physical footprint of these AI processors is totally maxing out, so the future of hardware engineering is literally going vertical. Industry giants like Intel, TSMC, and Samsung are actively pioneering 3D IVR. Instead of placing power components side by side with the logic cores, they're using advanced techniques like hybrid bonding to stack a dedicated power delivery die directly beneath the compute die. This achieves true zero-distance power delivery. Power comes straight up from the bottom, exactly where it's needed, saving precious real estate and drastically improving efficiency. Ultimately, we are witnessing the birth of the Unified Power Delivery Network, or PDN. It proves that the relentless growth of AI depends just as much on this invisible, holistic redesign of power circuits and components as it does on raw computing speed. The processor and its power supply are no longer separate entities. They are one single, unified, optimized system. Which leaves us with one critical takeaway. As we push ever faster into the era of incredibly power-hungry AI, where a single chip demands as much electricity as a major household appliance, the true limits of computing aren't just about algorithms or transistors anymore. It's about who can conquer the physics of power delivery first. So, who do you think will win the race to perfect the 3D power delivery network?